It's time to start I²CNER webinar. Good morning, good afternoon, and good evening, ladies and gentlemen. Thank you for joining I²CNER seminar series. The I²CNER seminar series was launched in 2010 upon the inception of I²CNER. Since then, seminar series has featured the best researchers in the world on carbon neutral energy issues. I am Masanobu Kubota, professor at I²CNER. I will be the chair for the webinar today. I'm very glad to see many audiences on the screen, and I can see many participants from outside of I²CNER. Welcome to I²CNER webinar. Today we have the most famous scientist in the world in our field, which is fatigue and fracture materials. Before introducing him, we will have a few words from the director of I²CNER, Professor Petros Sophrons. Petros, please.
Thank you, Masanobu. Thank you for the introduction of our webinar. And let me say that this webinar is helping the mission and vision of I²CNER. We are engaging key members of the international community from academia, as we are doing today with Professor Robert Ritchie from UC Berkeley, from national laboratories, industry, government agencies, policymakers. We are working, by carrying out fundamental research to enable development of low carbon, high efficiency, and low cost energy systems that will help Japan on its way to achieve carbon neutrality by the year 2050. Again, as I said, I²CNER carries out, is engaged in many activities in order to enable this vision, in order to do its fundamental research, in order to outreach to the society, to collaborate and partner with industry, to collaborate and partner with organizations, with international institutes and universities all over the world. And this webinar is indeed one of our most fundamental activities that showcases some of the best research that I²CNER is trying to engage. So without further ado, Professor Kubota, please take it away.
Okay, thank you very much. Thank you, Petros. Before we begin, I'd like to take a moment to remind you that we will have discussion after the presentation. During presentation, please keep unmute. And this webinar will be recorded by I²CNER, but recording by audience and taking screenshot and photo of presentation are prohibited. Next, I'd like to introduce Professor Robert Ritchie to you briefly. As I recall, I met Professor Ritchie the first time at the international conference on small fatigue craft in 1998. It's 24 years ago. The venue was a hotel at the North Shore of Oahu Island, Hawaii. He organized a conference with Professor Yukitaka Murakami. He had a presentation on ultrasonic fatigue testing of TI alloy or superalloy. I don't remember correctly. Anyway, I gave him a question on the effect of temperature because temperature rises during ultrasonic testing. Okay, Professor Robert Ritchie is a HT and JC Chua distinguished professor engineering in the material science and engineering and mechanical engineering departments at the University of California, Berkeley, and the faculty is senior scientist at the Lawrence Berkeley National Laboratory. He holds a Master of Arts, Doctor of Philosophy, and Doctor of Science degrees in Physics and Material Science from Cambridge University. He has published more than 800 papers and is the author of the new textbook, Introduction to Fracture Mechanics from Elsevier in 2021. He is a fellow of the Royal Society and of the Royal Academy of Engineering in the United Kingdom, a member of the US National Academy of Engineering, a foreign member of the Russian Academy of Science and the Royal Swedish Academy of Engineering Sciences, and is a fellow of the American Association for the Advancement of Science. He is known for his research on the fracture and fatigue of engineering and biological materials. His talk today is about mechanisms of fracture and damage tolerance in new metallic alloys. So, Professor Ritchie, please begin your presentation.
Well, thank you very much, Professor Kubota. Thank you, Professor Sofonis, for a very nice introduction. And it's a great honor to be talking to the I²CNER community. So thank you very much for inviting me. I wanted to talk today about damage tolerance, and particularly in some of the newer metallic alloys. And I really want to talk about high entropy alloys or multiple principal element alloys, because they have become the rage, so to speak, of late, and they've almost put structural materials back on the map. At least in the States, we're actually hiring faculty in structural materials again, which is quite remarkable after a long dormant period somehow. But before I do that, I thought I'd look at some conventional materials first. So this is my plan of action today. I want to talk about what I believe damage tolerance is, and then talk just a little bit about traditional alloys, a little bit about bulk metallic glasses, because they're a little different in both cases, the examples I give, than what we normally understand as toughening, and then devote most of the talk then to high entropy alloys. And at the end, if there's time, talk a little bit about gradient materials, which is nature's way of doing it. So let's start with my notions of strength and toughness. I call these conflicts because in many cases, high strength materials have low toughness and vice versa. But I think you can look at toughness. It's obviously perceived to be the energy preventing a crack from causing fracture. But I look at it as a competition. And it's a competition between two classes of toughening mechanisms. The classic ones, which are the ones that are primarily used in ductile materials, I call intrinsic toughening mechanisms. They take place ahead of a crack tip, and they are basically mechanisms that inhibit damage. And the primary driver for this is plasticity. And that's why there's a conflict between strength and toughness, because high strength materials have less plasticity, and therefore there's less plasticity to engage in this intrinsic toughening. These mechanisms, as I said, occur ahead of the crack tip, and they primarily originate at the nanoscale, the scale of a Burger's vector or something like that. If you look at a brittle material, though, those mechanisms don't work, because a brittle material in the limit is defined as one where you break a bond at the crack tip rather than emit a dislocation. And there you have to operate what I call extrinsic or mechanisms. These operate primarily behind the crack tip or at the crack tip. And they are associated not necessarily with plasticity, although plasticity could play a role. They're associated with shielding. They are mechanisms that basically shield the crack tip from the applied stresses. And they carry load, basically, these mechanisms, which would otherwise be used to propagate the crack. And the classic ones are, of course, of bridging. You have bridges across the crack, they sustain load. Deflection at the crack tip is another mechanism. And if you're dealing with fatigue, then there's a wedging mechanism called crack closure. Now, these originate at any scale, mostly at the micro scale, but at any scale. And these are the mechanisms that operate basically to promote toughness in extrinsic, in brittle materials. In fact, there's not much other ways you can do it. But both these mechanisms, if they involve phenomena behind the crack tip, and of course, extrinsic are inherently behind the crack tip, but even with intrinsic toughening, as a crack glows, it leaves plasticity behind the crack tip. That can lead to what's known as an R curve or resistance curve. And if we look at the fracture toughness, I'm using a stress intensity here, which is, as you know, the amplitude of the stress field at the crack tip. And we plot it against crack extension. you get an R curve if you have a relatively tough material. And the initial point of the R curve is the crack initiation toughness, which people measure K1C, J1C. It's a readily measured parameter. But of course, if you stop there, you leave all this extra toughening associated with the stable growth of cracks. And this toughening is associated with the phenomenon behind the crack tip. Plasticity, if it's intrinsic toughening, or the toughening mechanisms themselves, if it's extrinsic toughening. And this is known as the crack growth toughness. And this is absolutely important from the perspective of damage tolerant. In the same token, you don't want a material like a piece of chalk that simply snaps when you break it. You want some ductility. That's basically a requirement for a structural material almost. Well, in the fracture world, it's that rising R curve that gives you that it's basically a parachute. Effectively, instead of just breaking when the crack initiates, you allow the crack to grow stably and generate toughness. So you'll see this in all these materials. We're trying to develop an R curve. Now, the fracture mechanics of the R curve, a little bit more complicated, not quite as robust as crack initiation, but from the perspective of alloy design, it's absolutely critical. Okay, so let's start with something a little bit old. I want to talk about steels, basically traditional alloys initially. And just to remind, before I get into this, there was a phenomenon that we looked at 20 years ago, 25 years ago, which we call delamination toughening, which has relevance to these steels now. These are aluminum lithium alloys. And prior to that, similar materials were the 2219 alloys, and they were used as the main tank of the space shuttle, which carried liquid oxygen, liquid hydrogen. And one of the characteristics of these alloys were they got tougher at lower temperatures. Now they're FCC, right? They're face-centered cubic. We don't expect a ductile brittle transition, but most alloys, even things like aluminum alloys, this is a plot here of the toughness versus the temperature. They sort of stay relatively flat. But this particular alloy, and these are the aluminum lithium alloys particularly, actually get tougher at lower temperatures. They get stronger, of course, but they get tougher as well. And the question was, why do they do that? And this is a kind of an interesting phenomenon you don't see a lot about. When you look at the fracture surface, you see these sort of delaminations on the fracture surface. And it turns out these alloys have a sort of pancake structure. It's a very, very layered structure. And if we look, this is called the short transverse orientation. If we propagate the crack down those layers, the layers are quite weak and you get a very low toughness. But conversely, if we propagated a crack in this orientation where the crack is growing perpendicular to those weak layers, you get what's called the crack arrestor orientation. That's like breaking wood against the grain. That's a very tough situation. Now, those two are pretty obvious, of course, but the one that's not so obvious is the other orientation where the weak planes divide the crack. And this is known as the crack divider orientation. And I've shown it here. And this is the orientation where these alloys really look the best. This is the LT orientation where you get the maximum toughness at liquid helium temperatures. And what happens is it delaminates along these planes when the cracks tends to break, and it's delaminating perpendicular to the crack path. But what that does is it separates the material from a plane strain fracture into a series of plane stress fractures. Because at low temperatures, these planes get weaker and it tends to delaminate. Now, you've all seen this plot of the toughness versus the thickness. There's a high, plane stress is very high, and then it drops to plane strain. Well, by having these materials delaminate into these little tiny, they're not quite plane stress, they're non-plane strain fractures, you get a series of toughnesses up here rather than a series of toughnesses, rather than one segment down in the plane strain region. It's a fascinating sort of phenomenon, a little different, that crack divider, you generate a series of tougher plane stress regions rather than a single plane strain region. Well, when we look at these new materials, for steels, a similar thing happened. These are called deformed and partitioned steels, and they were developed by Mingxi Huang at the University of Hong Kong. And his philosophy here was to make a very cheap steel with great properties. And this is cheap. It's got just manganese in, a little bit of titanium, a little bit of vanadium, a little bit of aluminum, but mainly a 10 manganese steel, very cheap. And he takes it through a very complicated series of heat treatments involving hot rolling and warm rolling and annealing. That's the difficulty, I think. There's quite a lot of things to do, but you end up with, again, a pancake type structure with these layers here, but it consists of both ferrite and austenite. And the austenite can trip to form martensite. So it's a bit of a trip steel. But if you look at the strength properties, this is the stress strain curves, you see you get pretty high strengths here, about 200 megapascals. Sorry, 2 gigapascals. And you don't get much strain hardening here, but you get a little bit of a rise there, and that's due to the transformation of the austenite to the martensite. And you can see an image of this here, not very clearly, but there is some transformation. But this is not the main effect, funnily enough. And if you look at the toughness, provided you're in the same orientation, and this is the R curve here on the right-hand side, you see you can get a very, very high rising R curve. This is done in terms of the J integral, but if you convert it to K, this gives you a toughness of 100 megapascal root meters, which is pretty good for a 2 gigapascal strength steel. Now, how does that work? Well, once again, you look at the fracture surface and you see these delaminations perpendicular to the crack path, and they're much steeper delaminations in this case. And it turns out when you look at them, they occur along the prior austenite grain boundaries. And it turns out you get manganese segregation to those prior austenite grain boundaries, and that weakens those boundaries. So the short transverse properties of this steel would be very bad, but when it breaks with the crack divider orientation, we get this very, very high toughness. We get a series of these plane stress regions rather than one plane strain region. Very interesting phenomenon. You can see these delaminations exactly the same way as the aluminum lithium alloy. Now, these delamination widths have got to put you in this region, so they've got to be the right size, and happenstance is okay here, but it still generates very high toughness, which is slightly increased by the trip effect as well. So I thought I'd throw that in because it's a kind of a different kind of mode. The other different, you can see here, this is a banana plot of toughness versus yield strength, and this pretty high toughness you can generate with these relatively cheap steels. Another interesting one, before I talk about high entropy alloys, is metallic glasses. Now, I don't do a lot of work on metallic glasses, but I'm firmly convinced that the majority of toughness data on metallic glasses, which is published in the literature, is actually wrong, but that's by the by. But anyway, you can get very tough materials with these very tough materials. Now, as you know, metallic glasses have this issue of forming shear bands, and a single shear band can basically reduce the ductility to near zero, and you get very, very low toughnesses and low ductility. But if you can generate multiple shear bands, the shear bands are in fact the form of plasticity. So if you get multiple shear bands and you can somehow arrest them before they cause complete failure, you can get good properties. And so this was first done by Bill Johnson and his student Doug Hoffman. This was a while back, but he put a second phase in so that he could basically stop these shear bands from getting long enough so they could cause failure. You want the shear bands because they generate plasticity, but you don't want them to get too long to cause failure. And the result was very high toughness. In the original science paper, the Nature paper they didn't measure the toughness properly, but we did a little bit later. And you get these great R curves now, and you're getting toughnesses up around 150 megapascal root meters. And these steels, these glasses have very good strength. But it's hardly a metallic glass now because it has this crystalline ductile phase in. So we wondered whether we could do this with a monolithic glass. And this was, again, a while back, but we generated a palladium silver containing glass, which had remarkable toughness. This, you can see an image of it now. It looks like mild steel. Very, very. This is a material with a 2.5 gigapascal strength. but it clearly has toughness. And our philosophy of doing this was very simple. We said, well, if we have a low, I think this is called a Pew ratio, a low shear to bulk modulus, the low shear modulus would promote multiple shear bands, but the high bulk modulus would prevent them opening to form cracks. And this worked. We got extremely high toughnesses. This is a fracture toughness R curve here. We're now close to 200 at the crack growth toughness with a 2.5 gigapascal strength material. Exceptionally good toughness. And if you look at this on an Ashby plot, this is fracture toughness versus yield strength. We're way out here, pretty high toughness material. So we thought we were wonderful. And then we started to look at different size samples. So we had this toughness of 200 here in a fairly small sample. We got the material from Germany and we looked at a bigger sample. And instead of getting a toughness of 200 megapascal root meters, we got a toughness of close to 20 megapascal root meters in the same material, but a different sample size. This is a much bigger sample size than this one. So what's going on here? Now, if you look at our data, this is a plot of the fracture toughness. This is a particular bulk metallic glass. We look at the fracture toughness versus the size of the sample. It's a ligament size. It's how much material you've got underneath the crack. Provided we have a big enough sample and linear elastic fracture mechanics applies, everything looks pretty good. But as soon as we get into the non-linear elastic fracture mechanics regime, the data is all over the map. And this is where we'd seen that 200 in the small sample and the 20 in the large sample. So we got this big change. So what's going on here? And I think we don't know precisely, but we think the reason is that when you're using linear elastic fracture mechanics, everything's fine. But when you go into the non-linear elastic fracture mechanics regime, remember, you have to have a Hutchinson-Rice-Rosengren field that's unique at the crack tip. And that field is a field dominated by strain hardening. It's that local degree of strain hardening that gives you the uniqueness that you can measure the toughness in that non-linear elastic regime. If you go to full plasticity in any material, then you know the fields just are not unique anymore. The bend fields and tension fields are totally different. But you can get away with it in the non-linear elastic fracture mechanics because of that zone of hardening. But of course, these metallic glasses don't have any hardening. They soften. The shear bands are softening. So we think that one of the problems here is that the extent of the HRR field in a metallic glass is extremely small. So the region over which J can be a unique parameter would be highly limited. There's another reason, though, which I think is very interesting, and that is the reason of what causes these shear bands. Now, in metallic glasses, if you anneal them, they become more brittle, and if you quench them, they become more ductile. And there's these phenomenon called rejuvenation, which seem at first sight to be counterintuitive. But what we have here is that, and this is a theory that came out of basically Evan Ma, that in these amorphous states, you get little motifs of atoms. They're little regions of icosahedral symmetry, five-fold symmetry, which make them stable. And these are basically motifs, and you can predict them and you can actually measure them. It's kind of difficult to measure them. But some of these little motifs of atoms are not quite as stable. They don't have as much five-fold symmetry, and he gave them the name geometrically unfavored motifs, or gums. And they're more loosely packed, and because they're unstable, they can trigger shear bands. So the irony of this is if you can get lots of gums in the structure, you can trigger lots of shear bands, and that leads to plasticity in these materials. These are basically MD simulations. In this particular composition, they're all zirconium copper. You just have a situation where you don't have many gums, and so you just get shear bands in one place, and you get a degradation of the properties quite considerably. It just necks down to nothing. But if you can distribute them throughout the structure, you can see you get multiple shear bands, And that leads to a degree of plasticity, because the gums are what lead to the shear bands, which lead to the plasticity. And you can change them with cooling rate. The irony is that, you know, when you have a slow cooling rate, you get a brittle material. When you get a fast cooling rate, you get a ductile material. Everything's back to front. So we tried to see if we could prove this by using electron microscopy, trying to look at some way of reducing that. So we could try and find that where the shear bands form are in regions where there's less icosahedral five-fold symmetry. And we use, this is work with Andy Miner at the National Center of Electron Microscopy. He has this 4D STEM technique where we can look at little tiny regions of atoms. They're of the order of about a half a nanometer, and we can look at columns of atoms and we can see the structure. But the key is we can move very quickly throughout a whole lattice because we have very fast detectors that can see these things. So we had a little sample with a hole in it here, and we pulled it in the microscope, and we tried to see the regions of where there was less icosahedral symmetry, where there was more gums, and whether they were the regions where the shear bands formed. And you can see the predictions first. This is the predictions of where the shear bands are forming, and of course they're forming where you'd expect. We're loading it, you know, in the vertical direction here. But if we look at the regions of local icosahedral ordering, that means where the gums are the greatest, they form in the same bands. So it does seem to be a tie-up between shear banding and these gums. Now, this is a prediction. We tried to look at it in the microscope. This is not as clear, but I think you can convince yourself that you can see the regions of strain again at 45 degrees or nominally 45 degrees. And we think we can make out in this region here, the lower degrees of order is where these bands should form. So it's a little bit of a chicken and egg argument, because when you form a shear band, you break the icosahedral order, but there is clearly a link there. So we think this notion of geometrically unstable motifs of atoms and the formation of shear bands may be the key to these very high toughness metallic glasses, because they can generate multiple shear bands and ductility. And you can see another simulation here of where the local strains are forming, and this is where the fractions of these gums are formed. The maximum fractions are formed in the same place. Anyway, those are two examples, I think, of a little bit more unusual damage tolerant mechanisms. Now, let me talk about high entropy alloys for the rest of the time. That's what I really want to discuss. You've all probably heard of these. We're talking about multiple principal element metallic alloys. And there are two types. I'm going to talk about both of them. I'm going to talk initially about the so-called FCC, face-centered cubic ones. Now, as you remember, these have been around for about 20 years. They were discovered in about 2004, I think, by Ye in Taiwan and by Brian Cantor in Oxford. And they both reasoned that if you have multiple elements, you could maybe find exciting alloys in the center rather than the edges of phase diagrams, or you could come up with this notion of configurational entropy overwhelming the enthalpy of phase formation to give you a single phase material. The field has gone beyond that now and looking into multiple principal element alloys. We don't worry so much about the entropy idea, although it does have some justification, but it's a much broader field. But the original alloys look very interesting. And this was one of the ones, this was known as the Cantor alloy. It's a chromium, manganese, iron, cobalt, nickel, equiatomic, face-centered cubic, although each of these elements has different crystal structures. When you look at these alloys, I'm sure you've seen this story before because it's quite old now, but we look at the engineering stress strain curve. This is at room temperature, this is at dry ice, and this is at liquid nitrogen temperature. And these alloys get harder and they get more ductile, which of course would be unusual for a body-centered cubic, but the degree at which this happens is quite unusual for a face-centered cubic. Now, we measured the toughness of these. This is the fracture toughness. And we found that the toughnesses, these are R curves again, they're done in the J integral. but the fracture toughness was above 200 megapascal root meters. Now, this is a material with a pretty high yield strength, tensile strength, about 1.2 gigapascals. So this represented a very interesting type of material, that it combines strength and ductility again, which gives it its high toughness. Generally, when you go to lower temperatures, the high strength means your toughness erodes, but this one, it gets more ductile. If you look at the structure, it's the simplest structure you could ever see. It's basically a single phase equiax grain size. There's no fancy microstructure in there. There's no precipitates that you can really speak of. But what you do find is that when you go to low temperatures, you get twinning, get nice twinning. But these were a new class of alloys because they were concentrated solid solutions. They tended to have sluggish diffusion. They tend to have a little bit more lattice friction to dislocation motion because there's different elements. But when we looked at them in the microscope, we saw the duality of deformation mechanisms, which speaks to the ductility and the strength. They're not in conflict here. So if you look at, for example, this is a planar slip band in this alloy, and you see perfect dislocations are moving along that slip band in a rather slow fashion, presumably because of the high lattice friction. But if we look at a somewhat higher strain, you'll see the same slip band, but look what comes in here. See that fast? That was a partial dislocation, which can move very, very rapidly. So we have mechanisms here, ponderous mechanisms, which give us strength, and these rapid motion of the partials that can give us some degree of ductility. And the result of this is you get strain hardening, because you get a different mechanism, initially dislocation glide and then stacking fault formation with partials coming in to give you further deformation. And this is what leads to continuous strain hardening. And when we get to lower temperatures, we get twinning, which is a third mechanism. Continuous strain hardening is the classic prototypical intrinsic toughening mechanism, because it hardens the material, but at the same time, it delays the point of necking and instability, so you increase the ductility. So these were really very interesting alloys. Now we looked at a separate one, a simpler one. We called this a medium entropy alloy, and this is just chromium, cobalt, nickel. We've left the manganese and the iron out. This is a stronger material, and now this is the tensile test at room temperature, 200 Kelvin and 77 Kelvin. We're up around 1.3 gigapascals. They don't have a great yield strength, by the way, but they have very high tensile strength. But we're getting 90% tensile ductility at liquid nitrogen temperatures, which is remarkable. Now the toughnesses are really high. The initiation toughnesses go from 200 to 273 megapascal root meters at liquid nitrogen temperatures. That's extremely high. And the crack growth toughnesses, what I call the steady state toughnesses, are up above 400 megapascal root meters. Now these are really big numbers. And if we look at the microstructures, there's twinning everywhere. This material, because it's harder, twins at room temperature. So again, we have this duality of mechanisms. You can see a twin band here. There's a twinning structure throughout the material. And these twin boundaries actually can arrest dislocations. This is the strengthening mechanism. The dislocation comes up and arrests against the twin boundary. We see the same planar slip bands, but if you look very carefully, particularly at low temperatures, you get massive cross slip coming out of those slip bands. So you've got the strengthening mechanisms. This is a ductility mechanism due to the cross slip. And the other thing that's intriguing is the twin boundaries themselves act as highways for the partial dislocations to move on. You can see the dislocations are moving along that twin boundary. So we again have mechanisms, a duality of mechanisms that promote ductility and promote strength. And of course, this generates strain hardening, which is the key to their very high toughness. Some other examples, just quickly, we did some work at liquid nitrogen temperatures. This was done by I²CNER former student at Berkeley who's at Zhejiang University. And you can see the twinning, multiple twinning forming. This is at 93 degrees Kelvin in the microscope. We get the same planar slip bands with massive cross slip coming out of it. You can watch dislocations impinge on grain boundaries and twin boundaries. That's of course hardening, but you can see the emission of twins and dislocations, which results from all this. So again, we have mechanisms that promote and mechanisms that inhibit dislocation motion. And the last one I think is very interesting is the motion of these dislocations along the twin boundaries themselves. This is a twin, and you can see these partial dislocations moving down these highways. So again, this is one of the mechanisms by which you can promote deformation. Very, very interesting. Now, there's some different types of materials here. This is a dual phase version, slightly different than the original Cantor alloy composition. Again, a very, very simple microstructure, but some of the grains are hexagonal. And when you deform this one, you get even higher strength. This is the dual phase. This is the Cantor, the original one. You get higher strength and higher strain hardening. And it's very interesting to see what you see. You see these stacking fault networks. And I can show you one here. These are these networks of stacking faults. And they are remarkable barriers to dislocation motion. One of the things that allow these to form is you see these so-called lomocotral locks, which are sessile dislocations in these alloys. It's when you get two partials come on two planes, intersecting planes, and form then a sessile dislocation. And these tend to pin these, make these networks very stable. And they really are stable. You can see dislocation slip bands coming up to these networks, and it basically stops them dead. So it's a very, very powerful strain hardening mechanism. So this alloy should be better, right? Should be even better, but it isn't. This is the original Cantor alloy. These are R curves, J integral versus crack extension. Red is warm at room temperature, green is dry ice, and blue is liquid nitrogen. And that's the one I showed you before, that you get this increase in toughness at liquid nitrogen temperatures. But when you have this trip effect to form the hexagonal, be it dual phase, or you can do it where it trips itself during the test, you get good toughness, but it doesn't get tougher at these lower temperatures. So it's a very similar composition. These two have the added mechanism of the transformation to form a hexagonal phase, but it's not as good as the original alloy, which didn't have so much of that. And the reason is that the trip effect is beneficial. It absorbs energy, it gives strain hardening, but the resulting phase is epsilon martensite, which is a brittle phase. So if you're going to have this mechanism, you don't want too much of it. You don't want to have too much, because that gives you an embrittled material. So what happens if we go to extreme conditions? I'll quickly go through these. This is looking at this same Cantor alloy at very high strain rates. We started off with a uniaxial compression at 10 to the minus 3 per second. Then we went up to dynamic compression, where we're up about 6 orders of magnitude. And then when we did the Hopkinson bar technique at about 7 orders of magnitude in strain rate. And so what we find here is we get very high strength. As you can imagine, we can get the strengths up as high as 4 gigapascals with this split Hopkinson bar. But we start to see all those mechanisms that I talked about, but in much greater magnitude. So we see a lot of twins, very, very fine twins forming, much finer than we saw at room temperature. You can see them here as well. And we also see regions of the hexagonal phase, but very little and in very, very narrow bands. And we see amorphous material. We actually form amorphous material at these very high strain rates. So we're getting ductilities of 50% at these very high strain rates, but we're getting yield stress, or sorry, ultimate strengths, which are approaching, well, over 4 gigapascal meters. So if we look at the toughness of these alloys, you don't measure a conventional toughness, it's absorbed strain energy, basically. these very highly strained alloys have the highest toughness compared to a whole bunch of other materials you might test. And it's a bunch of steels, marging steels, titanium, copper, and the like. So, excuse me. Again, it's this multiple generation of deformation mechanisms, and even now amorphous material, which sustains the strain hardening, which is the key. Now, the most recent stuff we've done is we went and did liquid helium tests. We went to the Engine X facility just outside Oxford and did the tests in liquid helium. We have to have big samples, so we're not getting 4 degrees Kelvin. We're closer to 20 degrees Kelvin, but it's pretty cold. And here is that 3-component chrome nickel alloy on an R curve, J versus crack extension. There's the original data I showed you for room temperature, dry ice, and liquid nitrogen temperature. And this is the one at the liquid helium temperatures. And we are measuring toughnesses here of 415 megapascal root meters. And we're measuring the crack growth toughnesses, which I call the steady state toughness up here, of 500 megapascal root meters. And to my knowledge, that is the highest toughness ever measured in a material. So there's something magical about these materials. And they are, remember, the simplest structure imaginable. They're just equiax grains, single phase. But we can get remarkable toughness. It's all ductile fraction. And if you look at the mechanisms when you get down to liquid helium, then everything is that much finer and that much more planar. You can see this is an EBSD, masses of twins everywhere. You don't even see dislocations because the stacking faults, the stacking energy obviously gets lower and the stacking faults extend dramatically. But this sequence of dislocation slip, stacking fault formation, twinning, and trip to form the hexagonal phase, but there's very little of that hexagonal phase. You don't get a lot of it. Seems to generate this remarkable strain hardening, which gives us these ridiculously high toughnesses. You can see the same effect in the 5-component, the Cantor alloy, but not to the degree we see in the cobalt chrome nickel alloy, which is a remarkably high toughness material. So these are very, very tough materials. And this is completely intrinsic toughening generated by prolonged strain hardening from a sequence of deformation mechanisms. There are fatigue effects as well. I'm going to bypass those because we don't have a lot of time. The thresholds in fatigue are higher at low temperatures and at low temperatures, but we don't think that's associated with necessarily what I talked about. It's more associated with so-called crack closure. But we do see evidence of twinning, and the twinning can cause crack deflection and things like that. So there is a big effect of this. But if you make the grain size coarser, you roughen the fracture surface and you get much better properties. This is the coarse grain structure here, fine grain structure here. Again, blue is liquid nitrogen, red is room temperature. But that's really a closure effect. So there's nothing particularly exciting about this. The crack propagation data is comparable or better than most comparable alloys. But the last thing I want to talk about is a little different, is that, you know, these are multiple principal element alloys, and these FCC structures show, I think, the most exceptional damage tolerance that we've seen in any material. And these special properties associated with these alloys, people talk about high entropy, of course, sluggish diffusion, severe lattice distortion, because you basically have different atoms, size atoms in there, but they generally refer to the randomness of the solid solutions. But a question we asked a couple of years ago is, are they random? Are there any unconventional atomic structures or elemental distributions, such as clustering or local chemical ordering, that might affect or enhance these properties? So the first thing we did is we did work on DFT, or density functional theory. There were some evidence from Oak Ridge on X-FACS, X-rays, absorption fine structure, which suggested that in these multiple principal elements, certain bondings was preferential. For example, the chromium atoms tended to prefer to bond to unlike atoms rather than like atoms. This is known as the Warren-Cowley parameter, and the chromium are disfavored, but the the chromium nickel and the cobalt nickel are favored in terms of preferred groupings of atoms. So we did we used basically Monte Carlo simulations based on DFT. Not too many atoms, unfortunately, but it takes too long. And what we found was that the presence of local order will naturally form as a lower energy state. But what effect does it have? We found it had dramatic effect on the stacking fault energy. Now, this was done for the chrome, cobalt, nickel material. And the computed stacking fault energy for the random solution is actually negative, which is always confusing because anybody who measured it would find it to be positive. And if it was negative, you'd expect the whole structure to be hexagonal, and clearly it isn't. But we found as you increase the degree of ordering, the stacking fault energy went from minus 43 to 30 millijoules per meter, which is a big effect. We also found that the stability of the face-centered cubic versus the hexagonal phase varied with increasing ordering. If you had a random solution, then the lowest structure, energy structure, was the hexagonal phase, which is consistent with this negative stacking fault energy. But as you increase the degree of order, it stabilizes the face-centered cubic phase. Now that's important because you don't want too much hexagonal phase. We also found that it affected the twin boundary energy. It affects the formation energy for vacancies and interstitials. And as I'll show you, we didn't do this, but Evan Ma subsequently did some MD calculations where it was found to affect the dislocation mobility, and it affects the slip mode. So this seems to be a pretty profound thing. The question is it really there? Yes, I think it is, but it may always be there. It may be ubiquitous. We don't know exactly. We don't know how to control it. That's the problem. But we think it may have an important role in this developing this sequence of deformation mechanisms, which is so inherent to the properties. So one aside here, in this alloy, often the local ordering is associated with magnetism as well. There is, if you put like spin atoms together, particularly chromium-chromium pairs, you get what's called magnetic frustration. So there's a magnetic component to the local ordering in these alloys as well. But let's see if we can see it. And this is what we did a lot of work on. The first work was done by I² in Zhejiang University, and she used this atomic resolution EDS and in the stem, and looked at basically the counter alloy, but replaced the element manganese by palladium. And the reason to do this was to get a different atom, which was have a different atomic radius and a different degree of electronegativity, to try and see if there's any change in order. And they do scans, and they're looking at columns of atoms, and they can get basically the concentration of those columns. It should be random. And in the case of the chrome, manganese, iron, cobalt, nickel, there's basically a randomness, you've got 5 elements, so it should be 20% of each element in each column if it's random, and that's what you see. But in the palladium one, we got tremendous variations, which in some cases varied from 20, should be 20% if it's random, but went from sort of 5 to 45. And so it's difficult to say that this is actually clustering. So these are concentration modulations which have some degree of periodicity. The periodicity the wavelength is about 1 to 3 nanometers, which is much higher than the normal short range order, which is basically nearest neighbor shells, but it's clearly a form of ordering, and it generates a rougher lattice. And if we can measure the atomic strain fields in these conditions, this is basically looking at the shear strains and the tensile strains, and there's basically a key here in the counter alloy where we don't see much in the way of these concentration waves. Then there's a small degree of positive and negative atomic strains. But in the one with palladium in, where we do see these concentration modulations over these 1 to 3 nanometers, then you can see quite a degree of positive and negative strains, which would act, they would roughen the lattice and act to possibly increase the strength of the material. A second approach was done to look at the more common form of local ordering, which is the nearest neighbors. This was done at Berkeley with Andy Miner again, in looking at an energy filtered TEM, where you basically have an inline filter which gets rid of the inelastic scattered electrons. You get a cleaner image. And we looked at 2 conditions, one where we quenched it from a high temperature, and that was presumed to basically have a random structure, and then we aged it at 1,000 degrees to generate short range order. Now that's easy to say, but there's a big tail behind that about whether there's order there or not. But what we see are these streaking of these spots, which is evidence of superlattice deflections. You put the aperture on one of these streaks, take a dark field, and you can see these basically little clusters of atoms. You can see the formation of them in terms of the fast Fourier transforms here. But if you map this out, we're seeing clusters of the order of about a nanometer, which are forming. And these are basically associated with what was originally seen by the XFAX and came out of our DFT, nearest neighbor interactions, the preference for unlike rather than like bonds. Now, that was, I think, the first direct evidence of local ordering in these materials. But more interestingly is what effect it had. We see in the quench structure, which is supposed to be random, as opposed to the age structure, which is supposed to have local ordering. You can see here, you get a change from wavy slip to planar slip. When we look at the spacing of the partials, which is an approximate way to get the stacking fault energy, in the material which has the random condition, then the spacing is larger, consistent with a small stacking fault energy. And in the case of the material which has the short range order in, then the spacing is smaller, consistent with a larger stacking fault energy. So that's completely consistent with the predictions of DFT. When we look at nano indentation, these are nano indentation curves of the nano indentation load versus the depth. What you're seeing here is the nucleation of dislocations, the initial nucleation of dislocations, and it certainly is occurring at a lower level in the material which has random compared to the material that has short range order. Now, we also measured a change in properties, macroscale properties. We got a change in yield strength and we got a change in modulus, but that is still a bit of a controversy because you may not get an effect on the macroscale properties. And we haven't got this totally sorted out yet, but we firmly believe now that when you get short range order, dislocations moving on these slip bands will tend to effectively annihilate that order. And we think that process promotes twinning. So we think short range order, and we're still trying to prove this, is implicit in this sequence of deformation mechanisms, which is so important to the strain hardening, which gives this material its incredible toughness. It may not affect the macroscale properties because we don't really know whether we can totally inhibit order when we water quench and generate it when we age. We don't understand the kinetics of this process yet, and that's the difficult part. So just last few minutes, there is a second type of high entropy alloys called the BCC materials. These are the refractory ones, and these are renowned for having very, very high strengths. This is yield strength versus temperature. These materials like molybdenum, niobium, tantalum, tungsten, and molybdenum, tungsten, vanadium, tungsten have much, much higher temperature strength than nickel-based superalloys. So they're potentially are very exciting materials. The problem is that most people have studied these in compression, which gives a false sense of security. This is the different alloys, titanium, zirconium, niobium, tantalum, aluminum. This is the test we did in compression. Look at the engineering strains here, up to 40%. If we do them in tension, look at the engineering strains, 0.15%. And it breaks nowhere near the yield strength. So these materials have very low tensile ductility, and they have a very high ductile brittle transition temperature. There's only 3 toughness results in the literature, by the way. One is on a bicrystal and a single crystal. One is on a material which is this niobium, titanium, tantalum, hafnium, and they claim the toughness was 211 megapascal root meters. If that's right, then that's worthy of a Nobel Prize almost, but I don't think it's right. But there is a big problem here with being able to measure these not to measure them, but they're very, very low. This is a bunch of ones we've looked at, and they hover around 2 to 4. Sometimes they get to 10 to 15. But compare that with the ones for the FCC alloys where we had toughnesses of 500. And part of the problem here is that they can embrittle in the boundaries. There's a big problem with decohesion in the boundaries. And the notion of segregation to the boundaries is now different because you've got 4 or 5 elements in there. And so the whole boundary can change rather than just an element going into the boundary. So this is a very interesting field to look at. So in the last few minutes, I'll just say the following. These alloys are expensive because they have multiple principal elements in there. And another approach, and this was suggested by Kay Lur a few years ago, is to use nature's approach, which is to put in gradients. You know, bamboo is stiff, but it's flexible and it's hard. And that's generated by changing the spacing of the cells across the diameter of the bamboo. It's a gradient. Nature does this all the time. It's difficult for us to put gradients in. It's kind of costly, but we've done this with using a technique that Yi Li who did this for us at IMR in Shenyang using electroplating with nickel. And we've generated gradients from a coarse grain, which is about 4 micron, to a fine grain, 30 nanometers, but in bulk sizes. People have done it in teeny sizes. We've done it now in centimeter dimensions. And what we find is we can combine strength and ductility seamlessly with these gradients. The fine grain, this is the fine grain structure, has very high strength. The coarse grain structure has very, very good ductility. And if you make these gradients, you can combine the best of both worlds. And depending on which way the gradient is going, you can generate very, very high properties. These are toughnesses here in just pure nickel with a variety of different gradients from coarse to fine to coarse, from coarse to fine, fine to coarse. And we're getting toughnesses up here of about 250 megapascal root meters in nickel. And you've got a strength level here in the gradient ones of well over a gigapascal. So this is an intriguing way to go. It's much cheaper in terms of elements, but you've got to make them. And that means you're going to need to use additive techniques and so forth. So it's beginning to become feasible, but it's a much simpler way to go. And if you look at how the cracks grow, the fine grain material, of course, gives you high strength. But in addition to this, or rather, instead of the strain hardening we've talked about before, in the coarse grain structures, you get this massive crack blunting, which is very effective for toughness. So again, a slightly different mechanism, but you can generate this combination of strength and ductility just with a simple nickel material, very simple. So let me conclude, but I've tried to look at some of the various ways to make high toughness, high strength materials, and that's what damage tolerance is. It's making high toughness without degrading the ductility. I gave some examples from steels and bulk metallic glasses because they're very different. But in these high entropy alloys, the FCC materials tend to be, I think, the toughest materials we've seen. This is the Ashby plot. There are the metallic glasses. They're very strong because they're amorphous, but these cobalt, chrome, nickel materials have some of the highest toughness that we've ever seen. To me, it's associated with a generation of a series or a synergistic sequence of deformation mechanisms, which kicks in at increasing strain to prolong strain hardening, which then generates both strength, but inhibits localization to give you very high ductility. And we think, although we don't have absolute proof yet, that the short range order, which may be ubiquitous in these alloys, or we may be able to control it, plays a critical role in triggering some of these effects, for example, destabilizing the hexagonal phase. And so I think the notion of developing alloys by tailoring disorder by order is an intriguing thought, but whether it's feasible, we don't know yet. And finally, I've just thrown out the fact that you can get pretty good properties, certainly strengths and toughnesses, which are not quite as high as these high entropy alloys, but still very good, just with simple alloys, if you can generate gradients. And gradients are a way of combining properties, and oftentimes unusual combinations of properties. But the problem with those is the ability to make them. But I think with some of the new techniques that are coming out in processing, this is going to be very feasible. Thank you very much for your attention. Thank you.
Thank you very much, Professor Ritchie. It's very nice, very interesting talk. The materials are very different from that we used our study. So I expect many questions from audience. So do you have any questions? If you have a question, please use raise hand button on the bottom of the screen, please. So I have one question. Today you show the mainly effect of low temperature on the toughness and strength. But now I am studying hydrogen enrichment, hydrogen effect. So I'd like to ask you about the effect of environment, particularly hydrogen.
Yeah, this is an excellent question. There is work now going on corrosion of these materials. Corrosion, I think, is difficult in multiple principal element alloys because of the essence of corrosion, of course, is the films that form. And when you've got 5 or 6 elements in there, you don't quite know what's forming. So it's always a little difficult. But in hydrogen, some of these alloys, from the basis of what we've seen, others have seen, I must say, is they tend to have maybe a little quite good hydrogen resistance. One of the things that intrigues us is that hydrogen, if you believe the ductile help mechanism, hydrogen, in whatever it is, in promoted local instabilities, that is exactly the opposite of what these elements do. The multiple elements delay an instability, and the help mechanism would promote an instability, and that's the effect of hydrogen in the ductile case many times. And so that's an interesting thing to look at. The other thing is that there is evidence, although it's not overwhelming, that hydrogen further lowers the Stackenfeld energy here, so may promote twinning and so forth. And so these things, I think, have been seen, but they haven't been fully sorted out. So I think, but the general impression is that these materials may be pretty good from the point of view of hydrogen brillament. However, there is evidence of intergranular decohesion in certain alloys. And so I think the biggest problem that hasn't been solved yet is just the simple notion of segregation to a boundary. When we think of hydrogen brillament, you think of hydrogen in decohesion goes to a boundary and stays there. Or if you think of temper and brillament, maybe it's a sulfur or a phosphorus atom or antimony atom. But here you've got lots of different atoms, and maybe more than one goes to the boundary, and maybe it forms a different structure at the boundary, much like the ceramists talk about, complexions and so forth. So that's another issue that's never really been sorted out. I think the effect is more pertinent, though, in the BCC materials, because they, at high temperatures, you do have to worry about grain boundary decohesion. And in most of the alloys that we've looked at, the BCC structures at high temperature fail intergranularly. So solving that problem may help deal with their very high ductile roll transition temperatures, but this is really not known yet. But these are very interesting topics which are beginning to get people to start to look at them now, because there's, but I think the most pressing issue is in the BCC materials.
Thank you very
much. By the way, I don't think the stainless steels are pretty, I mean, are the sort of the ultimate for corrosion resistance. And I think some of these face-centered cubic materials with cobalt, chromium, and nickel will approach stainless steels. Whether they'll be as good, I don't know, but they'll be good, I think. But
thank you very much. So do you have any questions?
Somebody raised a hand here.
I cannot see.
Motonori Watanabe.
Sorry.
Motonori, please go ahead.
Yes, can you catch my voice?
Yes.
Yes.
Oh, thank you very much. I have a question about, yes, this is very interesting with the materials. I also have a question about the environmental effect. So this high entropy alloy is kind of the combination with the metallic materials. So my question is, if not hydrogen, if oxidized reaction is occurred, can we keeping of the high entropy like oxidized materials, or segregation and changing of the component?
Well, I mean, I think what's in the name, I don't think the original definition was equiatomic, 5 elements, but now anything goes. I mean, I think you can put in as many elements as you like. Oxygen, I think, in the BCC materials can form oxides on the boundaries. We've seen evidence of nitrides. And so I think with the corrosion problems, the choice of elements is more important. The composition is really important. In the toughness issue, the microstructure doesn't seem to be so important if you think about it, at least at the micron scale, because everything is just equiax grains. So we've looked to a lower level, which is the local ordering. But when it comes to corrosion, I think composition is very much more an issue. And I think with these BCC materials, when you're looking for very high temperature strength, but you're also looking for low temperature ductility, the refractory alloys have terrible corrosion resistance, as you know, terrible oxidation resistance. And so the choice of alloys will be very important. The choice of elements will be very important. And people now are trying to find different combinations of elements that somehow, you know, are okay from the point of view of oxidation, yet can still give you strength and toughness. So it's a difficult, you know, it's looking for the needle in the haystack in some respect. But I think there's, as one of my colleagues said, when you have 5 elements, you've got more dials to turn. You've got more ways of manipulating the structure. So I think this will be a very fruitful area in general, but I'm not sure that answers your question. But it's not so important that everything's equiatomic and that you can have 3 elements, 5 elements, whatever you like. It's this notion of getting away from the single element structure that we've lived with for so long.
I see. Thank you very much. Because of currently I have studying about the semiconducting materials. So therefore, like this of the materials of environment changing of the component is very interesting. Therefore, I asked. Yeah. Thank you very much.
Well, you know, this was originally brought out for effectively structural materials and metallic structural materials, but people are talking about high entropy ceramics now. And those ceramics are being used for all sorts of applications, for catalysis, for there's coatings to surfaces, all sorts of different applications have been brought out. So I think one wonders why wasn't this done before, but it just wasn't. But I think this is open Pandora's box in some respects, and something will come out of it. But it's a very intriguing thought.
I see. Thank you very much.
So does anyone has a question?
Masanobu.
Please, Petrus.
I've got a question. Professor Ritchie, thank you. Thank you for this lucid presentation indeed. Thank you so much. I learned a lot today. I'm sure everybody in the audience feels the same as I do. Regarding these FCC high entropy alloys, because essentially they don't have any microstructure like traditional alloys. So is it possible that the presence of the short range ordering activates the motion of dislocations into planar slips? And then once the dislocations are activated into planar slip modes, then all the other mechanisms have to follow up. Could there be something like that?
Yeah, I mean, that's exactly what we're trying to prove. I think we think that the problem is we don't really know if the local order is always there. We've had splat quenched material now, which has been quenched the fastest as you can imagine, and you can still see some evidence of superlattices. Now, if you anneal that material, it becomes 100 times stronger, but we don't know that we can totally suppress short range order. But we think, so we might not be able to control it, but it may be always there. And we do think that it does help this sequence, which is so important. Because you don't see this, you see individual mechanisms in in traditional alloys, but you don't see this perfect sequence. So as I said, we think the local order seems to generate planar slip. When a dislocation moves on a planar slip band, it will destroy the local order behind it. We think that triggers twinning. We're trying to prove that now. And once it triggers twinning, and then presumably at a higher strain, you'll get the transformation to the hexagonal. And then the short range order tends to destabilize the formation of too much hexagonal. So the keys are there. We don't have it put together perfectly yet, but that's exactly what we think, that local order is sort of instrumental in generating this remarkable sequence of deformation. You can't do it at the grain size level, so you're doing it at the atomistic level, which is a kind of intriguing thought. But whether you can control that by check is another issue. If manipulating local order may not be possible. We don't know.
Mm-hmm. And does this have any relation also, for instance, the triggering of subsequent triggering of the twinning within the context of our classical understanding of twinning? Classical material system twins after it exhausts its capability.
Yeah. But the other thing about it is that you see more twins in these materials. And we think that's associated with the fact that, a twin is formed by a partial dislocation moving on a slip band, right? In a regular alloy, every slip band's the same. But in a high entropy alloy, you've got 3 to 5 different elements. So every slip band is not quite the same. And some may be harder to form than others, right? And so there's evidence that instead of twins simply amalgamating to form bigger twins, which you see in a lot of traditional alloys, you get multiple twins formed everywhere, and they don't grow as much. So you've promoted nucleation because you haven't got a uniform sort of slip band. This is a notion that's been pushed by our former postdoc, John Ding, and he's done the MD calculations on that, and it does seem to suggest that's the case. It's a question of proving it, of course, but there are differences here, though, and so things we take for granted, like just twinning formation, may not be quite the same here in these, when you have this array of elements. And how much local ordering affects that, no one knows, but you can see how it might, right? That's another tantalizing concept to think about. So anyway, that's what, currently the short range order community in the high entropy alloys either think it accounts for everything, or it doesn't exist and accounts for nothing. And I think both those opinions are wrong, but somewhere in the middle is what's actually happening.
Yeah, intriguing. Yeah. I ought to say, may I comment about what you said about the HRR dominance for the bulk metallic glasses. Yes, that was such a physical argument. Amazing. You lose hardening, then you lose J dominance, which is
well, that was,
so
you know,
nice.
that's what McClintock always hated about J, because he always thought in terms of the fully plastic fields, right? And so, so you begin to realize that that presence of that HRR field is absolute necessity to get a unique driving force, a unique governing parameter. And you don't have that. So I think there probably is a region of J dominance, but it's so narrow you never see it. So the variability in the toughness of metallic glasses, I think, is a problem, because I don't think you could ever use them as a real structural material, because you wouldn't be able to specify one of the major properties. So, but I also think that of all the toughness measurements that have been made on metallic glasses that are published in the literature, probably 60 to 80% of them are wrong. So anyway, that's my opinion.
Yeah, thank you very much.
Is everything clear?
Column. The next reaction, that means reaction 4.
Do you have any questions? If not, please.
There is one question. Ivan?
Yes, thank you. Can you hear me?
Yes.
Thank you, Professor, for such a nice talk on a broad range of topics about high entropy alloys and even metallic glasses. I also want to ask a question about short-range order influence on various parameters. You showed us how short-range order can increase stacking fall energy. And I wonder, if I'm not mistaken, on some other slide, you showed us how it decreases stacking fault energy. Is it so?
No. It decreases the spacing. When you measure the stacking fault energy, it's not exactly the way to do it, but you measure the spacing of the partials, right? And if the spacing of the partials is small, the stacking fault energy is large. And if the spacing of the partials is large, the stacking fault energy is low. And that's what I was measuring. I don't think what I said was on the slides. It was right. I may have said it wrong way. I don't think I said it the wrong way around, but there's no conflict there. The DFT MD the Monte Carlo simulations predicted that huge change, and it's exactly the same as what we measure. That where you have a random solution, then the stacking fault energy is low, and when you have a one with short range order, it increases the stacking fault energy.
So yes, this was actually my question. So you predict that in almost any high entropy alloy, you would expect increasing in stacking fault energy with shorter order, because we are studying BCC medium entropy alloys, and we are not sure yet, but from calculations, we might see decrease in stacking fault energy, very small, but that's why I'm asking. Is it possible?
Yes, that's interesting, because we've looked at we've done limited work on looking at how local ordering affects the BCCs, mainly on dislocation mobility. We did a little bit on piles barriers, but most of it was done with an MD calculation. And we found that on certain situations that it can actually make dislocations move faster rather than slower when you have local ordering. But we weren't so concerned about it, because when you go to higher temperatures, which the BCC materials, of course, are geared for, you tend to, that difference due to local ordering tends to disappear, as you might expect. But yes, the situations, you get different effects on screw dislocations versus edge dislocations, so that we don't fully understand that yet. But we haven't, there's other problems, I think, with the BCC materials that we're looking at, which is their low toughness and their grain boundary decohesion. But the story is not quite the same as the FCC, you're right. It wouldn't surprise me you get the opposite effect.
Thank you very much for this answer. Also a short question about metallic glasses. You talked about importance of various local shapes like icosahedra. But I've seen some other studies focusing on more smaller effects, like effects of bond breaking and bond creation, which might be more important than these icosahedral structures, which are not very strong as it appears to me.
Yeah, it could be. I honestly don't know the answer to that question. I like the Evan-Ma theory because it, you know, a lot of the phenomenon in metallic glasses is sort of counterintuitive, but it seemed to fit together with this notion of local regions of instability. But you know, a lot of people talk about nanostructure in glasses, like Lindsay Greer. I've always thought it was saying the same thing, only with different words, but you may be right. It may be down to not a medium degree order, but right down to bond breakage that can do it. I honestly don't know the answer to that question, but again, it wouldn't surprise me because these regions of less symmetry, I think it makes sense that they might promote shear bands, and that's, to me, that's the key to the good damage tolerance of these materials. But you know, in regular materials, there's many ways you can generate plasticity, so it doesn't. It could be, as you say, something due to a smaller scale. Who's doing that work, by the way?
There is a group, Professor Egami and
Egami, yes, I know. Yes, I know that work. Yeah. Yes. Okay.
Thank you. I understood.
Yeah.
Yes.
I know that work, and I think yes, that's perfectly feasible. It certainly is. But what do they call those atomistic atmospheres or whatever it is or something? I think, yeah, I have to look at that again. I'll look at that again.
Thank you very much anyway for this vivid presentation and your answers. Thank you.
Thank you very much for a nice discussion. This is almost the last call for question because it's time to close the session. Do you have any questions? So if no, shall we close this seminar? Pedro, do you have any comment?
Well, today my only comment is to thank Professor Ritchie for helping us elevate the rigor and visibility of our seminar series here that we have in I²CNER. Professor Ritchie, thank you very much for offering to give this presentation. Thank you.
Ross, it was my pleasure, and I thank you for your kind words, and thank you, Professor Kapota, for inviting me. Appreciate this. Thank you very much.
Thank you very much, Professor Ritchie. So I will close this seminar. Thank you very much. So bye-bye.
Bye-bye.
Yeah, we have good discussion. Thank you very much.